Hello, let's do a problem from your lab assignment, section 6.4. This is problem number 3. A tank is full of water. Find a work W required to pump the water out of the spout. So the spout, use 9.8 meters per second squared for G, the gravitational acceleration. Use 1,000 kilograms per cubic meter as the weight density of water. Okay, so let me just see if we can picture the idea behind pumping water out of a tank. So let's see, this is we're going to look at the x-axis as the height from the ground of the tank. And so what I'm going to do is I'm going to move the x-axis a little bit. I'll move it over here. And what we're interested in doing is pumping the water out of the tank. And so what we're going to do is let's go take a peek in here and get some water out. So what we want to do is take a slab of water. A slab. What does that mean? So I'll take the slab of water and we'll assume that slab of water is has some thickness. We'll call it delta x, and it has some height x, somewhere between 0 and 3, x sub I if you want. And so from here we're going to find the force of this water, and then we're going to pump it up. So we're going to need to know the distance that this thing has to travel to get pumped out of the spout. And so our spout. We're going to do this for different slabs of water. This is one slab of water. And there's another slab of water, just for an example. Now there's infinitely many slabs, but this slab is a little bit smaller than the other slab. So this guy is down here a little bit with a different distance and a different volume or weight. So that's the idea, is to pump these waters up above through the spout. And given that the water's container is 3 meters high, and then there's an extra 2 meters that the water has to travel, it goes all the way up to 5 meters from the ground. Okay, so let's that's a general idea. Let's see what kinds of questions will help us get through this problem. It says here, a layer of water that's delta x meters thick, which lies x meters above from the bottom of the tank, will be rectangular with length 8 meters. So the length of this thing is 8 meters. So let's take a look at one of these slabs, for example. This slab has a length of 8 meters. Now, as you go up and down the tank, you'll see that the width of these things will change. So what we want to do is we want to figure out what the width is as dependent on the height. So this is the relationship. This is it looks like it's a triangle that has base 3 and height 3. And so if this is the value of x, if we're at this depth over here, x, we want to know what this distance is. And then it looks like we have a height of 3 and a base of 3, so the height is x, then the base is also going to have to be x by similar triangles. So I think this first one should be x meters. So now the mass of a layer of water is approximately equal to the density, which they want us to use 1,000 kilograms per cubic meter, times its volume. Now it says approximate volume because the delta x over here it has a thickness, but the thickness doesn't conform to the shape of the tank. And so we're just going to assume that it's an approximation. So it's going to be the density times the volume. So we need to figure out the volume, and the volume of a slab, if we know that the if we know that the length here is 8 and then the height here is x, then it looks like the volume should be 8 times x. And then the delta x is the thickness, so that gives a rectangular box-like slab, which again, it's just an approximation, so that's fine. And then the 1000 is the density, so if you multiply the density times the volume, you're going to get the mass in kilograms. So let's check this answer. So now we have the mass, the force required to lift this layer, this one slab of water, the force that's going to lift this one slab of water is going to be the mass times acceleration. We have the mass already. The mass is 8x delta x times 1,000, so that's 8,000x delta x. And then we're going to multiply it by the gravitational pull. So it looks like that's all we're going to need is 9.8. So now we have this one slab of water. Let's take a look at this slab of water. So we have one slab of water at the height x. And so the next question is, to be lifted up to the top of the pump's piping, the layer must be lifted a distance equal to what? So this is an x value, and then we have to go up to the 5th tick mark here in your x-axis. So we want to know what this distance is. The distance is just going to be the largest minus the smallest, so it's 5 minus x sub I. But here they're going beyond generic, so I think that's just 5 minus x. If we were going to be technical about it, we would put this expression in a Riemann sum, then we would use x sub i's, and then we would add up a whole bunch of things, but they're not being too technical about this. So what can we say about the work required to move this one layer above? So it looks like maybe they've multiplied 9.8 and 8,000 to get 78,400 x times delta x. And so I think the only piece of information, so this is the work, remember, is equal to force times the distance. So this is the force, this is the mass times acceleration that we found, and so the distance that we're going to travel is just the distance that we had just found, which is 5 minus x. Now for different x values, you'll have different distances, you also have different masses, so that's going to be taken care of here. So therefore the total work required is going to be the integral from here, from 0 to not all the way to 5, because the water stops at height 3. So remember, this is supposed to be the water, the tank that's full, but the tank only goes up to 3. The extra 2 meters is the piping on top of the water storage. So we're just going to go from 0 to 3. And our integral has a constant that can be taken out, and then we have just a regular nice polynomial. So now we have an integral to integrate. We can leave that constant out in front, and we integrate this expression, 5x minus x squared. So 5x is going to be 5x squared, and we'll divide that by 2. And then we have a minus sign, and then integral of x squared is going to be x cubed, and that's going to be divided by 3. Okay, so we're going to put the value of 3 in here. It looks like we're going to get 3 squared is 9. 9 times 5 is 45. 45 divided by 2. And then we're going to need to simplify this, but let's just work this out right now. 45 divided by 2, and then we have 3 times 3 is 9 times 3 is 27. 27 divided by 3 is 9. So this is just going to be 9. We want common denominators here. Oh, when you put 0 in, you're going to get 0, so that's no big deal. That's no issue for us. So common denominators, we got 18 over 2, and then 45 minus 18 is 30, 20, 7. So it looks like this could be 27 over 2. So now we're going to need to multiply this by 78,400 times 27 over 2. We take out our calculator and just say 78,400 times 27, and let's go ahead and divide that by 2. It looks like we have what do we have? We have 1,058,400, and so that's the work. So the work done is going to be exactly what this number is, and J here stands for joules. That's the units when you mix the mass times the distance. So this is 1,058,400. Okay, so the rest of this stuff was just the integral part and getting a numeric answer for your definite integral. But the difficult part, remember, is setting up and getting the idea of these slabs of water. We want to find the volume of the slab multiplied by the density. That's going to give us the force. And then once we have the force, we look at the distance that this thing has to travel to go all the way up to the top, and then we integrate, because our force will change because our volume changes, and our distance also changes as you go up and down and taking different slabs of water. I guess they call it layer instead of slab. So we're looking at pumping different layers of water up to the height that we're pumping to. Okay, so I hope that makes sense. If not, you can just repeat the video and maybe take a look at a few other examples, either in your textbook or online. Good luck.